Hi there, welcome to my channel Mandu to Fundu. In this video, I'm going to discuss about the solution for snakes and ladder problem. Let's look at the problem description. We are given an n by n matrix board where the cells are labeled from 1 to n square in apostrophe on style, starting from the bottom left of the board and alternating direction each row. So if you see, it goes like this. So basically we start from the square 1 and roll the dice, which has one of 6 possible values. So depending on the value, we move to a particular cell. So when we reach the cell, if there is a ladder, we go to the target location where that ladder takes us. And if there is a snake, we have to reach the tail of the snake. And we have to find the least number of moves required to reach from this cell all the way to the last one, which is 36 in this for this board. This is a picture of the board, but to use that in the program, they have given the same board as a n by n matrix, and so in that the -1 means when we reach that cell, that is the final destination. But some of them have a non-negative one number. For example, in this case, which is so for example, for the cell 14, so when we reach here, instead of being in 14, it will take us to 35. That's what it indicates. So whenever we visit a cell, if it is -1, we will stay there. Otherwise, we will have to pick up the target value as the final cell. The game starts from the square 1, meaning the coin is already placed on square 1. So whenever we roll a dice, it starts the next moves will be starting from 2 to 7. So when we roll the dice, one of the 6 values leads us to one of these 6 cells. Let's look at the approach to solve this problem. So we are given this board, and we have to find the shortest distance starting from the cell 1 all the way to 36. Okay, so for this, the expected output is 4, because from 1 we can reach 15 when we roll dice 1. So when we roll 1, we reach 15 because it reaches the position 2, and because of the ladder, it goes to 15. From here, if we roll number 2, we reach here, but because of the snake, we go back to 13. And from here, we roll 1, we catch a ladder and go to 35. And from here, if we roll 1, we go to 36. So the path is 1, 2, 3, and 4. We can model this problem as a graph problem. Let me explain why. For this game, when we are in the cell 1, and if we roll number 1, we reach 15. So the next possible position is 15. Then if we roll number 2, we reach 3. If we roll number 4, we reach 5. If we roll number 5, we reach 6. If we roll number 6, we reach 7. So each cell we can consider as a vertex, and the cells which are reachable from them are neighbors, one level away from it. So in this case, from cell 1, the 15, 3, 4, 5, 6, 7 are one of the positions we can reach by rolling 1 to 6. Same way from 15, when we roll 1, we reach 16. When we roll 2, we reach 13. When we roll 3, we reach 18. This is 4, when we reach 19. 5, we reach 20. 6, we reach 21. So this is the next level, 2 level from the starting node. And when from 13, when we roll number 1, we reach 35 because of the ladder. And when we roll 2, we reach 15. When we roll 3, we reach 16. When we roll 4, we comes back to 13 because the snakes pull us back to the position 13. When we roll 5, we reach 18. When we roll 6, we reach 19. Okay, this is at the third level. And from 35, when we roll 1, we reach 36. So we reach the final destination. Okay, so there are 4 levels. That is the expected output. So how can we find the number of levels to reach that particular node? We can do a breadth first traversal on this graph. So in order to do the breadth first traversal, we need to have a function that gives us the list of neighbors for any given cell. Okay, but we are given the board as a matrix, but unfortunately, because cells positions are changing alternatively, we cannot straight away use this matrix to compute the list of neighbors. One more issue is if we have a row and column index as the value in each cell, it would have been straightforward to get the list of cell. But in this case, this contains the number of cells it is away from the starting point. So we have to again convert that into a row and column index, which will complicate our code logic. Okay, so the simplest way is if we trade space, then we can convert this matrix into an array where each cell in that array will tell us what is the final destination cell we can reach when we land in that particular cell. For example, here the cell, this is starting this is a 1, cell labeled as 1. So in the move list array, we have that number 1. But for when we land in the cell labeled as 2, this will take us to the 15. So we store that value in that index. So wherever the -1, we just simply put the corresponding cell's position number, but wherever there is a -1 value, we put that value. So eventually we have the list of next move. So at any given cell, the next move will be one of the 6 positions which are following that cell, and the actual neighbors will be the value present in those following cells. We have to consider that as the neighbors. For example, in this case, minus is for the cell 1, 15, 3, 4, 5, 6, 7 are the neighbors. Okay, so they are present in the next 6 cells in that array. Whenever we want to get a neighbors list for a given cell label, we have to simply read 6 positions which are following that particular cell. So it will be very easy to write code for this. To find the minimal number of moves to reach the final cell, we have to do the breadth first traversal. In that, we have to maintain a distance array for each cell. So whenever we reach a particular cell, we have to add 1 to its parent cell, and we put that value in the corresponding cell in the distance array. Finally, at the end of the breadth first traversal, entry for the final cell in the distance array will contain the number of moves required to reach that cell from the first cell. Let's look at the flowchart. Input for this procedure is matrix called board. First we convert that matrix into an array where each entry contains the final destination for that particular cell. Then initialize the visited array and distance array and the queue. So the visited array and distance array are of equal to the input size. Then add the starting vertex to the queue and mark that starting vertex as visited, and then initialize the distance for that in the distance array with value 0. Then we are entering the outer loop. This loop will run until the queue has some element or the queue not equal to -1. So if there are any elements in the queue and still we haven't found the minimum distance is not yet set, then we dequeue the element from the queue and we get the list of neighboring vertices for that dequeued node. Then we process all the neighbors. We go through the neighbors list and we dequeue one at a time, and then we check whether that neighbor is already visited. If it is already visited, then continue to process the next node. If it is not visited, then mark that node as visited and update the distance for that neighbor node by adding 1 to its parent's distance value and assign that for the current neighbor node, and then add the neighbor to the queue so that the next level nodes we can pull in. After doing that, we check whether the current neighbor we are processing is the last node. So if it is a last node, then we simply assign the distance of that last node from the distance array to the min dist variable and then break out of the loop. So when we go to the outer loop again, the outer loop will also break. Otherwise, if there are any elements in the queue, we keep processing. If either queue becomes empty or the min dist variable is not equal to -1, then we break out of the outer loop and we come out and return the minimum distance variable. Let's move on to coding. First, I define the constant for the visited and not visited state. Next, I write the function for build move list. This will convert the 2D matrix into an array. Next, I initialize the move list, an integer array, which is of size the number of elements in the matrix plus 1, because we want to have an entry for number 36. So I allocated extra 1 space. Next, I initialize the running counter idx with 1, and then left to right a boolean variable. This indicates which side the column 0 presents. First, I start reading from the bottom row left to right, because the left to right variable is true. And I initialize the left variable to 0 and the right variable to the last column. So if left to right is true, that means we can use the left variable as a column index. So we are checking the board of I of left equals -1, then we can we assign that current idx value as the value of that position. Otherwise, whatever the non-negative 1 value present, we assign that. If the left to right is false, in that case we have to use the right variable as the column index to read the data from the matrix. So we check whether that is equal to -1. If so, we just simply assign the current idx value as the target move position. Otherwise, whatever the non-negative 1 value is present, we assign that. And then I increment the left variable and decrement the right variable, and also increment the idx, and finally I return the move list array. After every row is processed, I toggle the left to right boolean. Next I'm implementing the snake and ladders function. First I build the move list, and then I initialize the visited array. This will keep track of which node is visited and not visited. And then the distance array, this gives the distance of individual nodes from the starting node. Basically it has the number of levels from the starting node. And then I initialize the queue. Next I add the starting node to the queue. So the game starts at the position 1, so I added 1, and then I mark the distance for that node 1 is 0, and then I mark the node as visited. Next I write the outer for loop, which runs as long as there is an element in the queue. And inside the loop I first dequeue the element and then update the queue. Then I derive the minimum and maximum move for the current position. So it is ranging from current plus 1 to minimum value between the current plus 6 and the length of move list array. Next I get the neighbor nodes from those range and check for each move. I get the corresponding neighbors from the move list array. And then I check whether that node is already visited or not. If it is not visited, add that neighbor to the queue and then mark that as visited. Then update the distance array by adding 1 to the distance of the parent and assign the sum as the distance of this neighbor. Next I check whether the current neighbor is the last node. If it is the last node, then return the distance of that neighbor, and finally return -1. This is for an error case. If there is no path, then we have to return -1. Next I am going to run the test cases. Okay, there is some compilation error. I rerun the test again. Okay, all the tests passed. Next I am going to submit this program. Cool, this program is accepted. Next I am going to do code walkthrough with sample input. The game board is given as a 2D matrix. As I explained earlier, it is hard to get the neighbor list using this 2D matrix. Instead, if we convert that into an array, wherein each element in the array will tell us what is the final position we can reach for the move that landed to that particular position. For example, when we are starting the game in position 1, if we roll the die and we get number 1, we get the final destination value by reading this entry. So the current position plus 1, and use that as an index in the move list and get the final destination for that move. So every cell will give what is the final destination for that move. Whenever we move to a particular cell, the corresponding value in the move list will give us the final destination of that move. First, we build this move list, and then we initialize the visited an array where we mark whenever a node is visited, and then the distance array which contains the number of levels it is away from the first node, and then a queue which will hold the intermediate nodes while we are traversing the graph. First, we add the cell 1 to the queue. The game starts from cell 1, so we added the cell number 1 to the queue, and then mark the node 1 as visited in the corresponding entry in the visited array, and then distance will be set to 0 because distance from starting position to starting position is 0. So now we are entering the outer for loop where we dequeue the first element in from the queue. So in this case it is 1, and every time we dequeue an element, we calculate the positions, the minimum and maximum moves that we can make from that position. So we get the range by adding 1 to the current node, current element's value, so which is that starting from index 2 plus current node plus 6 up to 7. So the next 6 elements in the move list array contains the neighbors of this node. Okay. So in this case 6, 2, 8, 5, 6, 10 are the neighbors of the node 1. Okay. So once we get that range, we try to read the final position when we make a move from here to here, and then we get the neighbor. So for when we roll number 1, when we add to the current position, we get 2, and we read that value in the move list. We read the value pointed by that index from the move list array. Then we get 6. Then we check whether the 6 is already visited or not. So in this case 6 is not yet visited. So we mark that as visited, and we updated the distance by adding 1 to its parent's distance value, which is 0. So 0 plus 1, 1. So we are adding distance 1, and we mark the node 6 as visited. This is in the iteration 0, inner loop iteration. And then the second move is to the position 3, where the final destination is 2, the neighbor. So the neighbor will be 2. We check whether the 2 is already visited. In the picture in the previous iteration, we can see that 2 is not yet visited. So we mark that as visited here and updated the distance by adding 1 to its parent's distance. So it will become 1. And then we add the 2 to the queue. And then in the iteration 2, the next move is to 4, position 4, which takes us to the position 8 in the board, and we check whether that is visited already. It is not, so we mark that as visited and updated the distance. The next move is 5, which is the final destination is same as that position, and we mark that also as visited and the updated the distance. Next move is 6 node, so which is already visited, so we skip this node here. Then the next move is 7, where we land in the cell 10. We check whether 10 is already visited. It is not yet visited, so we mark that as visited and then we updated the distance. So 6, 2, 8, 5, 10 are in the queue right now. Once that is done, we come out of the inner loop. Then we do continue with the outer loop with iteration 1, wherein we dequeue the first element from the queue, which is 6. So the possible moves from 6 is 7 to 12. So from min move is current position is 6 plus 1. Maximum move is minimum of current plus 6, which is 12, and then length of the list. So whichever is minimum, that 12 is minimum. So from 7 to 12 is the range. Okay. So in this case, when we move to the position 7, the final destination is 10. We check whether that is already visited. It is already visited, so we skip it. Then 8. It is already visited, then we skip. Then 9. It is not yet visited. So in that case, we mark that as visited. So that's what we are doing. And then we add 1 to its parent's distance. So the parent is 6. So parent's distance is 1. So we will add 1 to this and then update that as the distance of the node 9. Okay. And then the next is 15. So the position 15 is not yet visited. Okay. So we mark that as visited here and we add 1 to the parent's distance and update 2 as the distance for position 15. Next, 13. 13 is also not yet visited. So we updated, we marked it as visited and then add 1 to its distance and then set 2 as its distance from the starting node. So at the end of outer loop iteration 1, we get 3 new nodes in the queue, 9, 15 and 13. And then in the next outer loop iteration 2, we dequeued number 2. So the possible 6 moves from 2 is ranging from 3 to 8. So we read the final destination from the move list for those positions and check whether they are already visited or not. Depending on that, we take action. So for example, here 2 is already visited, so we skip it. 8 is already visited, we skip it. 5 is already visited, we skip it. 6 is already visited, we skip it. 10 is already visited, we skip it. 8 is also already visited and we skip it. So in this iteration, no new elements added to the queue. And then the outer loop iteration 3, we dequeue the first element 8 and the possible moves are ranging from 9 to 14. And we read the corresponding value from the move list to get the neighbors and check whether they are visited already. In this case 9, which is already visited, and 15, which is already visited, and 13, which is already visited, 2 already visited, 13 already visited, 14, 2, which is already visited. No new elements added to the queue in this iteration. Then in the iteration 4, we dequeued the element 5 and the possible moves from this position 5 is 6 to 11. Okay. and for 6 it is the final destination is 6, and we check whether it is already visited. Yes, it is, so we skip it. And then 10 it is already visited, so we skip it. And then 8, which is already visited, we skip it. 9, which is already visited, we skip it. And then 10 is the final destination is 15, which is already visited, we skip it. And then 11, it is 13 is also already visited. So for this iteration also there is no new elements added to the queue. Then outer loop iteration 5, we dequeue the node 10 from the queue. Possible moves are 11 to 16. We read the value for the position 11, so the final destination is 13, which is already visited, so we skip it. And then 2, which is already visited, we skip it. And 13, which is same 13, so we already visited, skip it. 14, 2, which is already visited, we skip it. 15, 1, which is already visited, we skip it. 16 is 16, same, so it is not yet visited, so we can mark it as visited. So the 13 to 13 to 1 are already visited. Okay, so I skip that diagrams for that. Then we come to the iteration 5. At that time, so we check whether the 16 is already visited, not yet, so we mark that as visited. And then we updated the distance for the 16 by adding the distance of its parent, which is 15. So the distance is 1 plus 1, 2. So we mark it as 2, and then we check whether that current neighbor, which is 16, is exactly equal to the last positions in the array. So in this case it matches, so we return the distance of the neighbor 2, so which is the expected output. Next I'm going to do the time and space complexity analysis for this solution. Time complexity for this procedure is order of n. So at most n elements needs to be processed to find the minimum distance to reach the last square. So the number of moves depends on the position of the ladder and the snakes in the board. In any case, we make sure the node is not visited multiple times. So at most n elements needs to be processed. So that's why the time complexity is order of n. The space complexity is also order of n because we use move list and visited array and distance array during the traversal. All these data structures of size n, which is the input size. So that's why space complexity is order of n. In addition to that, we also use the queue, which vary depending on the degree of the node, the next level nodes. So the space complexity is order of n. Thanks for watching this video. Have a great day.